All right. Well, thank you all for being here. My name is Ramses Garcia. Today I'm going to talk about completely positive maps. And these maps are fundamental in the study of sister algebras and in general in the study of operator algebras. I'm going to cover pages 55 to 62 of the notes. And the goal of this lecture is to introduce the concept of being completely positive, give examples, and present two fundamental theorems. At the end, I'm going to sketch a proof of one of these theorems. So feel free to ask at any moment. So before starting with the definitions, I would like to talk about some motivations for studying these maps. Things that you already know is that every element in a sister algebra is a linear combination of four positive elements. So, in particular, you have that the span of the positive elements generate all the sister algebra. And in some cases, when you want to prove something about an arbitrary element, a first step is to prove it for a positive one and then use linearity to conclude for all the elements on the sister algebra. So the positive elements keep a lot of information and important information. Another thing that I would like to mention is that the GNS construction starts with a positive linear functional and then produces a representation of the sister algebra. Yep. So you start with a positive linear functional, a construct a representation, and these allow us to import a lot of tools from Hilbert's space theory. And the last thing I would like to mention about positivity is that when we are working with sister algebras, a natural map to consider between them is um, star homomorphisms. The problem with the star homomorphisms is that there are not that many. Having a star homomorphism between sister algebras is kind of rigid. You already know that a star homomorphism that is injective implies uh, isometric. And also, you already know that every star homomorphism is contractive. So, if we want to study sister algebras and compare different sister algebras, we would like to have some maps that we can always assume that there exist, at least in some cases. Um, I'm going to mention another thing about star homomorphisms. As I mentioned, you can have, if you have A and B sister algebras, the set of star homomorphisms could be zero. For example, if we take uh, B equal a matrix algebra, the matrices over the complex numbers, and A any infinite dimensional as a vector space, simple sister algebra. What that means is that the sister algebra has no closed ideals. For example, you can consider A the compact operators. So in this case, the star homomorphisms from A to B are just the trivial one. And this is a problem. This is a easy fact to check since we have a simple sister algebra. All the star homomorphisms are necessarily injective, but this is a finite dimensional vector space. This is the motivation. Let's begin with the definitions. Right? You all have already worked with this algebra, but I'm going to mention, maybe I'm going to repeat things that you already know. So please tell me if I'm going slow. But if you have a star algebra, we can define the matrix algebra over A. And this is a vector space. And if we equip it with the matrix multiplication, we get an algebra and has a natural involution given by applying the evolution in each entry and consider the entries in the opposite way, just as in complex numbers. So we have a natural structure of a star algebra and the matrices. This is a star algebra. Okay. Let's fix some notation. Um, if you have a linear map phi between star algebras, we define its amplification phi n between the matrices over A and the matrices over B, and we define it as entry-wise. If you have a matrix, you evaluate it entry it, doing it by each entry. This map is called the matrix amplification, and we will use these maps to define completely positive maps. An exercise is the following. We already know that if we have a star algebra, then the matrices over that star algebra is again a star algebra. What happens if the star algebra is a sister algebra? Do we have a sister algebra structure? So assume we have a sister algebra using theorem 7.1, the theorem Gelfand-Neyman theorem. We can represent A on some Hilbert space, and we can represent it faithfully. Let's fix a star homomorphism that is injective, and we can consider its amplification. This is an exercise, and I should have written this is an isomorphism. And therefore, we have again we have uh, an exercise, and it is that its amplification Pn is an homomorphism. This is the exercise 10.2. And since P is injective, its amplification is going to be again injective. Then we can define a norm just by using this star homomorphism. Since it is injective, we have a norm, and since we have a star homomorphism, this norm is a sister norm. With this norm, the matrices become a sister algebra, and it is an interesting fact that this construction doesn't depend on the star homomorphism P. As long as it is injective, we can take another representation. Okay. Um, Definition. Let's consider a map, a linear map between sister algebras. We are going to say that the linear map is positive if it maps positive elements to positive elements. If n, I should say that n is a natural number. If n is a natural number, we say that phi is n positive if its amplification, phi n, is again positive. And we say phi is completely positive if is n positive for every natural number. We are going to abbreviate being completely positive just writing CP, and a completely positive map that is also unitary is going to be abbreviated as UCP. I didn't wrote it down, but if a completely positive map phi that is contractive. That means its norm is less or equal than 1, is said to be CPC. So we are not going to use this concept today, but it is a very important concept. A lot of properties of C-star algebras are stated using completely positive maps that are contractive. So that's why I'm saying that. We have two basic properties, but important ones. If you have a positive map between C-star algebras, then that map is bounded and that map is star preserving. Um, so you have that phi, and this only assumes positivity. In the last slide, I wrote down the norm of phi. This makes sense because it is positive. The phi is positive. So positive maps are always continuous. Um, we have two examples. The first one, we already know it. Every star homomorphism between C-star algebras is completely positive. The reason, as we saw, this was the exercise 10.2, I guess. We know that for every natural number, the amplification of P is a star homomorphism, and in particular, every star homomorphism is positive. And by definition, since every amplification is positive, we conclude that P is completely positive. The second example is says that if you have a completely positive map and an element on the sister algebra B, then if you compress that element, um, you get another completely positive map. I'm going to prove this statement. So I have the statement here. This is the same. Define C as B, phi A, B star, and this says that if phi is completely positive, then so is C. So for the proof, we want to see that Cn is positive for every n. So let's take a matrix and assume that this matrix is positive. We need to show that its image is again positive. Observe that Cn on this matrix, by definition of amplification, this is just evaluating C entry. And by definition of C, this is just B, phi, A, I, J, B star. So we have this matrix, and our hypothesis, I'm going to go to the last slide. Our hypothesis is that phi is completely positive. Therefore, this matrix is positive, but we have that matrix. We don't have that matrix. Uh, we are multiplying by these b's. So this is equal to the matrix which has b on its diagonal and zero all on the other entries, and this other matrix and b star. So we have something of the form a positive element, and we are multiplying that positive element by the left and by the right by something like, okay, I'm going to say that again. You already know that if x is positive, then y star is again positive. And since this matrix by hypothesis is positive, we conclude that this is again positive. Therefore, we have shown that phi n is positive, and since n was arbitrary, we conclude that phi is completely positive. We have two more examples. If we have a positive linear functional, it is not that hard to show that it is completely positive. So we have, at the beginning, we start talking about how positivity is a key property in the study of sister algebras. And our concept of um, being completely positive generalizes being a star homomorphisms and positive linear functionals. This fact doesn't depend on the complex numbers. In general, if you have a positive function, a positive map between sister algebras, and one of them is commutative, then phi is going to be completely positive. So this is a class of sister algebras where we have that positivity implies completely positivity. Naturally, we should ask, are there completely positive, are there positive maps that are not completely positive? This is an example of such map. Consider the matrices, the 2 by 2 matrices over the complex numbers, and define phi to be each matrix send it to that matrix, the adjoint of that matrix. That this map is positive because if we consider a positive matrix x star x, this is by definition of phi this, and we know that that is x star x. So in fact, phi on the positive elements is the identity. A natural question is it completely positive? For this, let's introduce M, the following matrix. Um, let M be the matrix, be this matrix. If we identify the 4 by 4 matrices with the 2 by 2 matrices over the 2 by 2 matrices of the complex numbers, we have that M is equal to this matrix. I'm doing that identification to not write the parentheses. M is positive, and it is straightforward to check that, in fact, it is equal to this. But if we evaluate the amplification of phi2 on M, by definition of phi, we get this matrix, and a straight calculation shows that -1 is in the spectrum of that matrix, and therefore phi2 on M is not positive. I'm using here that an element in a sister algebra is positive if and only if its spectrum is containing on the non-negative real numbers. Since -1 is on the spectrum, this matrix is not positive. So we have found an example of a positive map that is not completely positive. As the name suggests, being completely positive is a property that is preserved in every level, in every amplification. I'm going to, now that we know a couple of examples, and I'm going to state two important terms when we work with completely positive maps. And we saw on the well, we already saw that if phi is completely positive, then we can consider phi completely positive and B an element on the sister algebra B. Then we can consider C defined as every element send to B phi A B star. And this is going to be again completely positive. This is an important example of something that we're going to see next. And sometimes this is called a compression. Uh, yeah. Um there is no standard terminology for this. I call this compression, but you sometimes assume B is a projection or B is positive to call it a compression. The next theorem um, tells us that all completely positive maps are of this form. So we're going to state it for a unit cell, but this theorem works for arbitrary sister algebras. We are working in the Unital setting because it is easier, but it is true in general. The theorem is due to Stein-Spring. It is the Stein-Spring dilatation theorem. And the hypothesis is that you have a unital sister algebra, a completely positive map between A and the bounded operators on a Hilbert space. And this theorem tells you that there exists a Hilbert space H prime, a representation P to the new Hilbert space, and a linear map, um, which is bounded between the Hilbert spaces, such that phi is the compression of that representation. In particular, we have this information for the norm of phi, and when phi is unital, B is an isometry, and B star is the projection onto this space. In this case, when phi is unital, we can identify H with a subspace, and this is written in the following form. This is a very important theorem because it tells you the general structure of completely positive maps. As I said at the beginning, there are very few star homomorphisms, but all completely positive maps are compressions of star homomorphisms. And we usually think that this new Hilbert space H prime, we usually think that it is bigger because of this case when phi is unital. I'm not going to prove it right now. I will leave the proof for the end, but I have a couple of remarks to say. In the case that P is unital, we can think of the representation P in the following form as a matrix where the first entry is phi of A and the other entries are uh, linear operators. And for when thinking about P of A in this form, we are using that H is contained in H prime as a closed subspace, and therefore we can see H prime as the direct sum of H and its complement, its orthogonal complement. Um, there is a, well, yeah. And that is the reason why this theorem is called the dilatation theorem. Uh, the second remark is that there is a non-unital version. If we have time, I'm going to mention a couple of things about the non-unital version. And we call P H prime B as time spring dilatation. And there is a way to define the minimal time spring dilatation. I'm not going to define it. You have to talk about density of some subspace. And under that density condition, this minimal time spring dilatation is unique up to unitary equivalence. So this is important because it, when you consider the minimal time spring dilatation, there is a canonical way to associate a dilatation. Okay, the last remark that I'm going to mention is that uh, the hypotheses of the theorem are that you have a completely positive map with codomain the bounded operators on a Hilbert space. So at first sight, it seems that we can only apply this theorem in very specific cases, but we know that every sister algebra can be embedded in some B of H. And if we have a completely positive map between A and B, we can use the Gelfand-Naimer theorem to represent B into some B of H, and then we can use Stein-Spring dilatation theorem. Um, this theorem, at first sight, may seem weird, but you already know a specific case of this theorem. When H is the complex numbers, you have a completely positive map. And we know that when we are working with linear functionals, completely positive and completely positivity and positivity are the same. And this theorem generalizes the GNS construction. Um, I'm going to talk about that well, maybe it's a good moment to talk about that. So what I'm claiming is that the Stein-Spring theorem is a generalization of the GNS construction. So let's start with the linear functional that is positive. As I already mentioned, this implies that that linear functional is completely positive, and we can apply Stein-Spring theorem to phi. We obtain applying Stein-Spring theorem to phi. We obtain a representation P on some new Hilbert space H prime, and we also obtain um, linear functional between the original Hilbert space, which in this case is the complex numbers, and H prime. Linear operator. So at first, this doesn't seem like the GNS construction, but if we define X as the image of 1 under B, then um, I'm going to go back to the last slide. Then phi has the norm of B, the norm of the square of the norm of B, and this is going to be x squared. And we define X to be the image of one. And moreover, if we consider P A on X dot product with X, uh, by definition of X, that is P of A V star V on one. So I'm just writing X as B1 and moving it to the other side. That's why we have B star. And this the Stein-Springs theorem tells us that this equals phi A on and on one, and this is phi A. Uh, so this is the one of the conclusion of the GNS construction. X is the cyclic vector that is given by that construction, and thus uh, the Stein-Springs theorem does indeed generalize the GNS construction. Okay, before proving it, I'm going to talk about another important theorem, which is Arvinson's theorem. Sometimes we are able to construct a completely positive map on a C-star subalgebra, and this theorem will allow us to extend the completely positive map to all the C-star algebra in such a way that the extension is completely positive. So again, this theorem is true in the general setting, not only the unital, but we are going to enunciate it assuming A unital, B a unital sister algebra, and phi a completely positive map between B and the boundary operators on a Hilbert space. Then this term tells us that you can extend phi to phi tilde, uh, where this new map is completely positive and extends phi. This term generalizes a theorem that you already know, which is the theorem of Crane, and which says the same, but changing H for the complex numbers. So you can extend positive maps into positive maps. In fact, the proof of Arvinson's theorem uses Crane's theorem. So this is a very important result, and we can think of this theorem as saying that B of H is injective in a specific category. So so I'm going to prove Stein-Springs theorem. Um, Here we have it. The Stein-Springs theorem assumes that you have a unital sister algebra and a completely positive map, and we need to construct a new Hilbert space, a representation, and a linear map. Okay. In the GNS construction, we start with phi. Well, the proof of the Stein-Springs theorem resembles the GNS construction, and that is why I'm going to um, go faster than usual. But the first step when you have a positive linear functional is to consider A with a new with some positive form, and then consider a quotient of A by some vector space, where these vector space are the elements on the sister algebra A, such that this element under the form are zero, and therefore this form is going to be an inner product on the quotient, and then you complete. that is the sketch of the GNS construction, as you already know, and we are going to replicate that. But instead of working with A, we're going to work with A tensor H. And again, we are going to make a quotient. So let's start with the proof. As I mentioned, the first step is define H prime. We start by defining the form. Define this form on elementary tensors. Well, we know that every element on this tensor product is can be written as the linear combination of elementary tensors, right? So we can define this form on elementary tensors A tensor H and B tensor K in the following way. Again, this resembles the GNS construction, and it is an easy exercise to show that this is a sesquilinear form. We want a Hilbert space, so this form should be positive, and that is what we are going to prove, that it is a positive semi-definite form. So let's take an element in the tensor product and show that that element under the form is positive. As I said, every element on the tensor product can be seen as a sum of 10 elementary tensors, and the elementary tensors are, yeah, we want to prove that this number is greater or equal than zero. So let's just write down what is this. By linearity, we can write down the sums outside the form. And then in this equality, we use the definition of the form. So we haven't done anything special at the moment. But our hypothesis is that phi is completely positive. So it this implies that Pn is positive for every n, in particular for this one, the n associated to our vector. And we want to use our hypothesis, and this looks like a matrix. At least there is a matrix behind this expression. Um, we already know this equality, and a direct computation shows that this is equal to the following inner product. We need to change the inner product. Instead of working in H, we work in Hn. Hn is again a Hilbert space, and this is equal to this matrix on this vector times this vector. But by definition of the amplification, this is equal to phi n on this matrix, and it is an easy exercise to show that the following matrix is always positive for every element A1 to AN. Is a positive matrix, and you already know by the positive, uh, yeah, in the positive, when you study positive elements, you show that an element, an operator on a Hilbert space is positive if and only if this is positive for every x in the Hilbert space. So Since phi is positive, this element is positive, and this is an operator on the Hilbert space Hn. By this criterion, we conclude that this is greater or equal than zero. Um, that is the idea of the proof, that that form is actually positive, and this is the precise step where completely positivity is used, because if you consider uh, another element, this n is going to be different. So we need positivity at every level. That was like the hard part. The next is going to be just replicate what you already know for the GNS construction. We conclude that this is a sesquilinear and positive form. We consider the subspace N as those elements that under that form are zero. And we, well, we need to show that this is a closed subspace of the tensor product. After that, we mod out by this subspace. And in this new vector space, the form becomes an inner product, an inner product. In the natural way, we define this new inner product uh, just by taking a representative and define H prime as the completion of this quotient with respect to this inner product. Um, that is the definition of H prime. I write it down here. And we now need to define P. For each element, A, we define P of A on A tensor H to N tensor H in the natural way. When we evaluate a tensor element, an elementary tensor, we just multiply on the first entry and extend linearly, because every element of the tensor product is a linear combination of elements of this form. A computation shows that uh, PA applied to N is contained in N, and therefore we can consider PA on the quotient, and this induces a linear map. Again, by the computations that I'm not writing down, we conclude that PA is bounded, and we can extend it to all the Hilbert space H prime, and we define the representation P just by sending each A to PA. Using the definition of the Hilbert space and P is easy. It's an easy thing to check that P is an star homomorphism. And here is the first time that I write something related to the unit. In the last slides, I didn't need the unitality. In fact, I don't need it. Everything that we have done works for an arbitrary C-star algebra, and you have, well, I just show you the first part of the Stein-Spring theorem in the general setting. In the case that the C-star algebra is unital, P is clearly a unital star homomorphism. The next slide is going to be the one that we use. In the next slide is going to be the argument that uses unitality. Okay, so we already defined H prime, P. Let's define the linear operator B. Define B in the natural way. You have an element H, and this is a completion of a quotient of a tensor product of A tensor H. So this definition seems natural. And one should prove that this is a linear bounded operator. And finally, the last part is to show that V star P A B is equal to Phi A. Um, to show this, we are going to use the inner product of H. Consider H and K elements on the Hilbert space, and note that this element, uh, taking the adjoint, is equal to this one. I'm just moving V to the other side. And in the following equation, I'm using the definition of V. Again, I'm using now the definition of P. P just is multiply the element for the element on the first entry. And we now use the definition of this inner product. And the last step is the definition of this form. I should have written down that this form is defined as passing this element, evaluating this element times the other, but the unity, multiplying by the unity doesn't change anything. So we end up with this. We can conclude that the first entry is the first entry, and thus we end up with this. That is the sketch of the proof of Stein-Springs theorem. And I would like to say that there are two ways to prove this theorem in the non-unital setting. Um, in the notes, there is uh, there is a possible path for proving it, and and in general, if you want to define V, but you don't have a unit, you first define VI using a approximate uh, unit. Yes. And you show that VI has a limit point, and that limit point is going to be your new P. I'm going to stop the record. That is all. That is everything that I prepared.